Hello, BC Calculus students. This is Mr. Johnson, and we're going to start section 8.6, which is on representations of functions as power series. So we're going to start with our sort of our main function, your kind of your best friend as we go through this process with power series. This particular function we studied a lot, starting really with section 8.2 when we talked about geometric series. And we talked about how this rational function 1 over 1 minus x is identical to the function, the infinite polynomial function 1 plus x to the first plus x to the second plus x to the third, and so on forever, as long as x is in between -1 and 1. So the way we began this process is that we actually started with the function 1 plus x squared plus x cubed and so on. And we said to ourselves, okay, well, we're studying geometric series. We know that this particular series has a starting value a that is equal to 1. We know that every term is being multiplied by x, which is the common ratio, which is r. And we know that if a geometric series converges, then the sum of that geometric series is a divided by 1 minus r. And so in this case, we have 1 divided by 1 minus x, as long as the absolute value of x is less than 1. Or another way to think about that is that x is in between -1 and 1, but it doesn't include either one. So here's what we have. This is really the sort of the parent function, or the main focus of what this entire section is on, which is this particular relationship. We know that the rational function 1 over 1 minus x is equal to 1 plus x squared plus x cubed, and so on forever, as long as the absolute value of x is less than 1. And that is what we're going to use as our beginning process as we look at some of these functions and determine whether or not we can write them as a power series. Okay, so that's the entire idea. Now there'll be some visualizations in class related to this in terms of what it means to converge, but remember, these two don't match infinitely, so they're not perfectly aligned in terms of a graph. They're going to map perfectly to each other on the interval -1 to 1. So it's just a really small section where this infinite polynomial is equal to this rational function. And that in and of itself is really amazing fact. And what we're going to do is try to take these functions and represent them in a similar way to this infinite polynomial, some sort of infinite polynomial. Okay, let's take a look at this, because really the best way to kind of go through this is to look at examples, try some examples. You're going to have to, at the beginning of this process, it's going to feel like everything is just kind of made up and it just doesn't seem like it might be connected. But the more practice you see, I think the easier it does become, and you really have to dig into it, and you have to try some of these on your own as well, obviously. But at first, it's going to seem a little bit strange. So in example 1, we want to look at the rational function 1 over 1 plus x squared, and we're going to try to represent it as a power series. I'm going to keep the one that we have sort of as our parent function in the top corner here. So we're going to try to figure out how do we kind of manipulate algebraically 1 over 1 plus x squared to sort of look like 1 divided by 1 minus x squared. Now, one of the things we're going to do, and I'm going to highlight this in the original one, is that we're going to let this x right here that I'm highlighting in red be sort of like a holding bin where it has possible representations that are not just x. It's kind of like a placeholder for other stuff. And what I mean by that is that, for example, we could take we could take 1 divided by 1 plus x squared, and that's what we're analyzing in this example, and we could write that or rewrite that as 1 minus the quantity negative x squared, because obviously those two are equivalent, right? Now, if you think about it, we have now sort of reassigned the x value that we see in the parent function, or the beginning function that we developed back in section 8.2, and now we are instead writing that as negative x squared. In other words, we have basically the same relationship. Notice how we have 1 divided by 1 minus. We have 1 divided by 1 minus, and now we just have a different item that we're subtracting there. But in essence, it's kind of the same type of relationship. It's just going to look a little bit different. So what we're going to do is take every one of the x's that you see in the original, the parent function, the starting power series that we're studying, and we're going to simply just substitute in our new placeholder in that area. So here's what we have. We have 1, which is our very starting term. We're not going to change anything there, plus x, but instead of x, I'm going to have negative x squared, plus, instead of x squared, I have negative x squared squared, plus negative x squared cubed, and that pattern would continue. Now, the nth term, we're going to call the general term, and that one, of course, is the same exact pattern, and of course, this continues for a really long time. So let me go ahead and highlight exactly what we did. So we took, and notice again, we have this similarity of the x, the holding pattern there, that x value is continuing through that starting power series, and now we're doing exactly the same thing as we've rewritten it so that we can come up with some sort of similar representation. So we're comparing these two rational functions. Clearly 1 divided by 1 minus x is not the same as 1 divided by 1 plus x squared, but we're rewriting it and manipulating it so that they're similar, okay? Now let's go ahead and simplify this down. So we have 1 divided by 1 plus x squared, that's what we've been analyzing, and that is 1 minus x squared, I'm just kind of getting rid of stuff here and simplifying, plus x to the 4th, minus x to the 6th, and so on. My general term is a little bit different. I'm actually going to write this as an alternator. I'm going to pull the negative out and make it negative 1 to the n, and I'm going to multiply that by x to the 2n. And that is the standard form that we're going to see when it comes to this general term. So I want to make sure that you get used to that. And that's about as far as we can simplify that down. So if we're being asked to consider a power series for 1 divided by 1 plus x squared, this would be one of the representations that we could form. Now, one of the questions would be, when is this convergent? Because obviously the original one in the upper corner is convergent in between negative 1 and 1. Because we performed only algebraic manipulation to this, so we just rewrote things by factoring a little bit and changing some of the signs, but the overall was the same as the original. We just kind of tweaked the way it looked. The interval of convergence will be identical because of the fact that we're substituting in the negative x squared. So in other words, this original is convergent for the absolute value of x is less than 1. Therefore, our manipulation in which we put negative x squared in for x would be algebraically, as we simplify, the exact same interval of convergence. Because again, the absolute value of a negative is a positive, and that x squared, as we simplify, because of the radius of convergence being 1, will not change. So we have the exact same interval of convergence. And we can maybe write that down. Interval of convergence is negative 1 to 1, and the radius is 1, just to make sure we understand all of the items that are going on here. Okay, let's try another example so we can see some more patterns here. Okay, we're going to look at the function 1 divided by x plus 2. And again, our entire goal is to make it look like one over 1 minus x. That's the whole idea here. So let's take a look at how to possibly do that. The first thing I'm going to do is I'm going to take, and I'm just going to switch these around simply because the x in the denominator of the one I'm trying to make it look like is on the right side. That's fine. That's pretty easy. Notice that there is a 1 minus x. I have a 2. I'm going to divide by that, or I'm going to factor out that 2 in order to get it down to 1. So I'm going to make it 1 divided by 2 times 1 plus x divided by 2. And then I'm going to play around with the signs again. This is really similar to that last problem where I have 1 minus a negative x over 2. And so it looks a bit more complicated. I'm going to write it one more time as just 1/2 like this. And hopefully what you can see here is that when I'm looking at, I forget the 1/2 for a moment. When I'm looking at this, it is 1 divided by 1 minus. 1 divided by 1 minus, and instead of x, I have negative x over 2. So we've manipulated it into the form that we want. I'll deal with the 1/2, but this is the key right here. Negative x over 2 is what I'm substituting in for x. So let's go ahead and take a look at how to do that. I'm going to rewrite the one that we're focused on. 1 over 1 minus x is 1 plus x squared plus x cubed, and so on. If you're wondering whether or not you should memorize that one, you should. The answer is you should. All right, so we have 1/2. Actually, you know what? I'll do the original here. 1 over x plus 2. We know, based on all the black stuff that I wrote, what we're shooting for is this final one. I'm going to take the 1/2 and I'm going to multiply everything that I'm going to work on here. So I'm going to first take, and I'll erase this here in a second. I'm going to take this and I'm going to substitute it in for every single x that you see right here. And then I'm going to multiply the whole thing by 1/2. Okay, so we're going to do a few things at once. Let's go back here. All right, so we have 1/2 multiplied by 1 plus negative x over 2 plus negative x over 2 squared plus negative x over 2 cubed. And of course, don't forget about the general term. That's a pretty common question on the AP exam. All right, let's go ahead and rewrite this a little bit just to make it look a bit more, I guess, normal. So we have just simplification here. That's going to be plus x squared over 4 and minus x to the third over 8. Oh, hold on. I think I said 4 and wrote a 2. And then we continue this pattern, of course. For the general term, let's go ahead and make it -1 to the n, because again, that's pretty standard. And then let's do x to the n divided by 2 to the n. I'm thinking that once we deal with the 1/2, that's going to change things a little bit. Okay, that looks pretty good. Let's go ahead and distribute the 1/2. So we get 1/2 and minus x over 4, and then x squared over 8, and x to the third over 16. By the way, you can pick however many terms you want. It's really common for the exam to ask for maybe 3 or 4 of the non-zero terms. So I'm just getting you used to writing a small handful of terms. Right here I have 4 non-zero terms. If you wrote 3 or 5 or something like that, that's fine. Don't get in the habit of writing 1 or 2 because it's not very common, and it also doesn't allow you to see the patterns form. Okay, on the general term, I have -1 to the n. However, I'm multiplying by 1/2. So I'm going to get x to the n divided by 2 to the n plus 1 when I apply that 1/2 there. Okay, and then that continues. So there we go. I think that's about as simplified as we can make that thing. So this is the power series that we just came up with for 1 over x plus 2 as we compared it to our parent power series. In terms of convergence, remember that our original is the absolute value of x is less than 1. We used algebraic manipulation to work on that. So in our case, we substituted in negative x over 2 for the x in the parent function. And so therefore, as we work on this, by multiplying by 2, taking the absolute value, we end up getting the absolute value of x is less than 2. So the interval of convergence is -2 to 2, and the radius of convergence is, of course, 2. Okay, that was the first two examples. Let's go ahead and move on to the next page. Okay, for example 3, we're going to piggyback on example 2. So if you notice, we have example 2 as 1 over x plus 2. This one is now x cubed over x plus 2. And what I want to show you here is that if we start with our information from example 2 that we just worked on for a little while, here it is. So you can look back, or you can just copy what you see here. And then I'll write down the general term. Okay. All right, so we have our information from example 2. We're simply just taking this function now and we're multiplying by x cubed. So think of it this way. You could take f of x and it's all about algebraic manipulation. So you could just say that this is x cubed multiplied by 1 over x plus 2, and it would be equivalent. And so what we're going to do is take 1 over x plus 2, which we know is all of this. Oops, didn't mean to cross that off. All of this stuff right here is the equivalent of 1 over x plus 2, and we're simply just going to multiply it by x cubed, which algebraically is what's happening in the problem. So when we do that, we get x cubed over x plus 2, which is x cubed over 2 minus, so I'm just multiplying every single term by x cubed. And then when we get to the general term, we have x cubed times x to the n. So we're just going to make that x to the n plus 3. And then we still have the 2 to the power of n plus 1. And then we just continue that pattern, okay? Through multiplication here, we're not doing any additional or change of substitution. We're simply just scaling this by x cubed, which means that in terms of the interval of convergence, it has the same interval as we had for 1 over x plus 2. So our interval is -2 to 2, okay? If we were to manipulate it by doing some sort of substitution manipulation, like we did for example 2, that's when the interval may change. We have to consider that. In this case, we're simply just multiplying. We knew the interval from example 2, so we're all set there. Okay, that does it for the first video. In the next video, we'll take a look at differentiation and integration of power series. Thank you.